Okay, thank you. So thank you very much for giving me a chance to present my work here. I'm actually very excited today, and also feel kind of honored to be among other privileged, like prominent speakers. So today I will be talking about our paper that was published in Science Robotics a few months ago, 2 months ago. Is a paper on a flying robot, right? The title of the paper and my heading here is a little bit different, but we are talking about the same thing. We're talking about revolving-wing robot, which with an efficient hovering flight. So let's get started. So the robot I will be talking about is what you can see here. It is a 35-gram robot with 2 wings, capable of flying for 15 minutes. Now that probably doesn't sound like extremely impressive if you are not so familiar with the flying robots, small flying robots in general. But let me give you an example that, for example, a commercially available quadcopter or quadrotor that weighs about 30 or 40 grams can typically fly for only 5 or 6 minutes only. So this robot can fly twice as long as those robots, right? So in order to actually make this happen or make it possible, I'm going to give you kind of a background on the process, how we came up with this robot. So talking about small flying robots, so people would typically think of drones or quadrotors, and there are 2 amazing videos here. One of them, I believe, will be presented later by Professor Fligiht. Right. So these robots are basically in the order of a couple 100 grams, right? It has 4 propellers. They are really kind of very simple in structure, but with that, it comes with really great exceptional maneuverability. They can fly and do acrobatic movement. They can work in swarms, flying through dense forest. That is extremely impressive. Or, for example, learn to fly despite the very turbulent disturbances, as you see on the right video. And the capabilities here, you'll see here, is state of the art. It's amazing. But it's enabled by what? It's enabled by intelligence, for example. The algorithm, deep learning algorithm that allows the robot to see and sense and build a map of the surrounding, so it doesn't crash into those obstacles, right? It's enabled by, for example, hardware components. They carry companion computers capable of doing simultaneous millions of computation at any instance, right? They also carry cameras, right? LiDAR sensor for seeing in real time the surrounding environment. Now, if, however, right, we scale these robots down, we want to make smaller flying robots, right? And we can look at the state of the art, right? At much considerably smaller scales, sub-gram scales, we talk about RoboBees, for example, right? On the left-hand side is the classic example of Harvard's RoboBee that was developed by, led by Rob Wood at Harvard, my PhD supervisor. And also on the right-hand side, what you see is a soft fly by Kevin Chen, who was also from the same lab, and he's now at MIT, right? So the work on the right-hand side, the differences between them is the left one is powered by piezoelectric actuators, not motors, and the right one is powered by soft artificial muscle or dielectric elastomer actuators. Now, what you can see here is totally different from the previous slide, right? The robots, they're much smaller. They don't fly the same way. These robots use flapping wings. They don't have actually vision. Actually, if you look at the robot, it doesn't seem to have anything. They're only actuators and a few mechanical parts. This is because it's still tethered, right? You can see the Y. It's still powered by an external power source. It actually doesn't carry any micro controller. So it has no processing power. So it's still controlled by a huge computer system that you cannot see in the video. And also it's using external motion capture cameras to actually perform the sensing, right? Now, but these are state of the art, right? And to some extent, you can argue that they're not that capable because they're not autonomous. They cannot operate by themselves, right? Despite that, with the scale, at this small scale, they also have advantages. For example, on the right-hand side, you can see a robot doing a somersault maneuver, flip, right? Or when it collides with the floor, doesn't give them any destructive damages, right? That comes with the scale. So the reason that you see that creates the style differences, the contrast between these two kinds of robots is actually the size or the scale. And it comes down to physics of scaling, right? And that, because of that, right, the physics of scaling makes flight actually at small scale much more difficult than at larger scale. Though even at larger scale, flight is already difficult because flying is very expensive. Meaning you actually need to use a lot of energy to create lift and stay aloft in the air, right? So if you look at this plot, I took this plot from a review paper from Nature in 2016. The plot shows flight times of aerial robots across different scales from about 10 grams to 1 kilogram. And what you can see in the trend is very clear, right? As the size, as the mass of the robot gets smaller, the flight time becomes shorter and shorter. And this is actually in a log scale. So the effect is actually very prominent, very pronounced, right? Now, at smaller scale, it's very difficult to fly. You cannot actually have much flight time because you cannot actually generate enough lift. You cannot carry more payload. This is why those small flapping wheel robots cannot actually have battery on board, cannot carry anything, because it's still very difficult to fly them because they're not very efficient, right? Now, so the reason for the difference, right, for the effect of scaling can be explained fundamentally from the characteristics of the fluids. So flying is about aerodynamics. It's about the movement of air or of the flow. Flight is attained by pushing the air downwards such that the normal force gives you lift, right? That keeps the robot in the air. So it's all about aerodynamics, all about flow. One particular number, right? One particular metric that distinguishes, right, aerodynamic flow properties at larger and small scale is Reynolds number. Reynolds number, if you have taken fluid dynamics course or mechanical, for example, if you are a mechanical engineer or physicist, you would know that Reynolds number is actually a ratio that captures the importance of inertial forces over viscous forces. Right? The inertial forces, what I'm talking about is mass times acceleration. And viscous forces, what I'm talking about is air drag, frictional forces, right? And it turns out that flow at smaller scale, or low Reynolds numbers, is because the flow is dominated by viscous forces, right? So at a smaller scale, we have low Reynolds numbers, right? This is actually because the ratio, the importance of viscous forces becomes dominant factor to inertial forces, meaning the proportion of energy is actually a big proportion of energy is lost in the flow in terms of heat or other losses, right? Makes flying at small scale difficult. And this is the underlying reason, right? So if you come back, so we want to somehow, for example, overcome this problem. We want to make flight at smaller scale more efficient. So we come back and take a look at this plot, right? And I'm gonna focus on something that is a little bit smaller in the order of 10 grams to 100 grams, for example, here, right? And I can actually look at them a little bit more closely, and then find that I can group them as rotorcraft here in the order of, say, 30 grams to 50 grams. And also flapping wing robots. They actually come from sub-gram size, which is not fully autonomous, to 20 or 30 grams, which is actually autonomous. Right? And you can see, what you can see here, very obvious, is the fact that flapping wing robots is actually sitting on top of rotorcraft, meaning they actually have longer flight time than rotorcraft when we compare vehicles at the same mass, right? The same vehicle mass, right? One thing you want to notice is also the size of this. Despite having the same mass, the same weight, for example, a rotorcraft that is 30 grams might have a vehicle span of about 10 centimeters, but a flapping wing robot that is about 20, 30 grams might be about 30 or 40 centimeters in the span, right? So the two different things. It comes from different, as you can see, propulsion mechanisms. So in order to understand this, I can tell you, right, it comes to two things. The reason for the differences, the main differences are due to two reasons. The first is called unsteady aerodynamics, and the second, okay, is called disloading, right? First, I'm going to talk about unsteady aerodynamics. Unsteady aerodynamics, okay, what does it mean, right? So a mechanism for lift generation of flapping wings is created by flapping the wing back and forth, as you can see in the video. This is taken, right? This is the mechanism used by insects, and maybe birds, but birds are a little bit different, right? So in 1999, Dickinson and Sanjay Sen, right, published this paper about that they use kind of a scaled up dynamic model, right, to actually make a huge flapping wing, but flap them not in air, but in some liquid to match the Reynolds number, and study the force generated by flapping wings, right? They find something very interesting, right? And I'm not going to go into the details, but let me give you some examples, right? So when we look at regular fixed wing aircraft or propeller blades, you find that the propellers or the wing or the airfoils, sometimes called, right, operate. They go through the air at very shallow, small angle of attack, meaning the angle between the wing and the moving direction is actually small, in the order of 10 to 20 degrees. On the other hand, when the flapping wing goes through the air, the angle of the wing with respect to the motion is as large, is huge, is between 45 to 90 degrees even, right? Now, for a normal plane, for a fixed wing plane, when the angle of attack is large, what happens is they get into the condition that is called stall, meaning it will lose lift. It will not generate lift anymore. The lift will actually decrease, and you don't want to get into that situation. However, flapping wing doesn't get into that situation. They still create lots of lift when the angle of attack is large. So this is called delayed stall. This is attributed by the fact that the wing is actually not just translating through the air, but flapping back and forth. And it creates phenomena is called unsteady aerodynamics. One of the key mechanism of unsteady aerodynamics is delay stall. So it makes flapping wing actually very efficient when the Reynolds number is small. So this is why you can see at smaller scales, flapping wing becomes kind of a viable platform to create flight, right? Because it helps, it utilizes this aerodynamics property. And this is about scaling when it works when at low Reynolds number, right? Another thing I mentioned is disloading. Disloading is something that if I want to explain what it is and why does it matter, I have to first define something that is called power loading. Power loading is a ratio of lift to power. So it's a metric, it's a direct metric for efficiency. High power loading means you need lower power to generate the same amount of lift. So high power loading means you are more efficient in actually generating lift. Now, according to momentum theory, which is kind of a very very kind of simplified theory that can be used to describe flapping wing, propellers, spinning wings, and everything. However, it's also a little bit simplified, so it doesn't actually include the scaling effect. So you can use this to compare different lift generation mechanism at the same scale, meaning maybe at the same magnitude of lift, for example. This, according to momentum theory, it says that power loading is proportional to the inverse of the square root of disloading. And disloading is the size of the wing or the propeller, the area of the wing or the propeller, right? It's the lift to the size of the wing, right? So if you want your robot or a flyer to be efficient, to have high power loading, you want the disloading to be small, meaning you want a large wing area. You want a large wing area. You want to have a big wing or big propeller for the same amount of lift, right? So two things, right? So if you come back to the previous page, right? If you compare rotorcraft and flapping wing robots, you can see that flapping wing robots work very well at small scale because of two things. First, it's using unsteady aerodynamics because of the flapping mechanism. Second, the wing is actually larger than propellers. The wingspan is much larger, meaning it has actually lower disloading, and therefore it will have higher power loading, right? So when we talk about, if we want to inspect disloading, I can plot a disloading of different things, right, as a function of mass. And again, lower disloading is more efficient. However, disloading doesn't include the consideration of disloading doesn't include scaling effects. So for example, in this plot here, I actually know that at larger scale, planes are actually more efficient than quadcopters. However, it has larger disloading, but you cannot make a direct comparison because they have actually different scales, right? However, at the same scale, you can see here, there's some overlap, right? For the same mass of hummingbird-like robots and quadcopters, you can see that hummingbird-like robots, they actually have lower disloading than quadcopters at the same mass. So this is why they can be more efficient. Now, in this plot, I have robo-bees and hummingbirds. I have fruit flies. And I still have one spot at the bottom here. And if you may guess, okay, that's actually maple seeds or samaras. So basically, those are rotating seeds. Right? So maple seeds turns out to be an efficient flyer, a very efficient flyer because they have very low disloading, right? So putting two and two together, sorry, before that, okay, I forgot one slide here. So maple seeds, okay, this is again a really outstanding work published, also made it to the cover of Science in 2009. So it's 10 years after the flapping wing paper, right? By Lenting, they also show that summer wings, right? When they fall, they rotate and they create lift. It's an unpowered flight. So they have very low disloading, but also in the meantime, they also operate at low Reynolds number. And because of the spinning motion, they also benefit from unsteady aerodynamics in terms of leading edge vortices, right? So summer wing actually is super efficient, not only because of the low disloading, but they also utilize unsteady aerodynamics. This is actually a little bit different from spinning propeller because the wings of Samaras operate at higher angle of attack, and also the size of the wings are also different. So they spin a bit more slowly, but in a way, it has unsteady aerodynamics as well. So these are the two key benefits of Samara wings in flight. So putting 2 and 2 together, so we decided, right, putting 2 and 2 together, we can probably create a really efficient robot that can fly. And this is the robot that you saw in the first slide, and this is we created, right? And this is why we say this robot is inspired by maple seeds or Japanese maple seeds or samaras, right? So this robot is 35 grams. It has 2 wings. Wings are the main lift generating mechanism. Now, the fact that it's only 35 grams, the wingspan, the span of the robot is actually huge. It's actually more than 60 centimeters. It's about 60 centimeters because the wings are huge. The wings are huge because we want to reduce the disloading, right? The wing loading. So to give you a highlight, right? This robot, this is the video of how it flies and slow motion. What you can see here is basically is a pair of wings that is spinning. So this Samara robot doesn't work like a quadrotor because a quadcopter typically used 4 propellers pointing upright to generate lift directly. Our Samara robot has 2 propellers, but they're pointing horizontally. Their role is for generating rotation. And with the wing rotation, we actually use the wings to keep the robot aloft to generate lift. Right, this is how it works, right? Which is of course slightly different from quadcopters, right? So in a little bit more detail, okay, I'm not going to be too technical, but I want to re-emphasize on the importance of power loading, right? So this robot, okay, if we want to make very efficient, we look at this metric, power loading, meaning we look at the amount of lift the robot can generate over input power. And when we talk about input power, we're talking about electrical input power that goes into the motors, right? Into the motors that drives the propellers, right? So lift, okay, is proportional to how fast the robot, to the square of how fast is a quadratic function of how fast the robot is spinning with some coefficient that depends on the size and the geometry of the wings. And the power, of course, electrical power is basically the current consumed by the motor and the voltage that drives the motor. So what we want to do is we want to maximize this power loading, right? A little bit more closely, how it works is the robot will have when you supply voltage to the motors and the propellers, they spin, they generate force, okay, thrust force, TP, that gives the robot yaw torque to rotate, right? So the yaw torque rotation is actually generated by the propellers, will overcome the drag torque created by the spinning wings, right? Which is also proportional to the square of the rotational speed, big omega here, right? So put 2 and 2 together, we have to balance drag torque generated by the wings with the thrust generated by the propeller, right? So, and everything, of course, depends on the wings, the profiles of the wing, which is characterized by the variables CT and CQ here. So in total, if we want to maximize the lift power, then we have to consider the factors CT and CQ, which are dependent by the wings. So we want to optimize this. We want to maximize this power loading. So in order to maximize this power loading, we created a physical model with parameters that we actually don't know that we have to be fitted experimentally. To do that, we try out, tested different wing profiles to find out physical parameters that would fit the model. The model is actually physics-based, not for example, involving deep learning and stuff, because we actually have pretty good idea of what's going on physically, right, in flight. So we actually use physics-based model to optimize the robot, and with the optimized configuration, so it turns out, okay, the power loading of the robot is about twice as high as regular rotorcraft of the same size. This is because, of course, like in a simplistic sense, large revolving wings. So with the first version of the robot that we optimized for, it comes with a small battery, 35 grams in weight. It can hover for 15 minutes, or if we actually use a slightly larger battery, the robot becomes 42 grams, but it can fly for 24 minutes, right? So just to give you a comparison, if you go out buy commercial drones from, say, DJI right now, you can buy a small one, 250 grams. That would fly for about 30 minutes, right? That would fly for about 30 minutes. So this robot obviously flies a lot longer than that, right? As you can see, right? So coming back, right? So how do we sit with respect to other robots? We can look at these two plots. Let me step back a little bit so you can see the stars here in terms of flight time. So we actually much higher. We are about 2 times as long. The flight time is about 2 times as long as other robots of the same weight, or of similar weights, right? As again, everything depends on size and scale. And of course, this is because of the power consumption of our robot is much lower. So when quantified by power loading, our robot has higher power loading, which is about 8 grams per watt. And of course, this is probably more comparable to robots that are larger, right? Now, we can have a robot that can fly and last very long. Okay, sorry, one thing just for completion, I am showing that this work, our robot, right, compared to flapping wing robots, also has much disloading. So this is one of the key reasons why the robot is more efficient, right? So with the robot that is able to fly, we still want to make sure that they can function, right? They can function, meaning we should be able to place a robot somewhere, anywhere that we want it to be. We want to do position control. Now, that actually turns out to be not overly complicated, but not straightforward either, because how this robot flies is also different from other flying robots that people are used to. For example, quadcopter or flapping wing robots, they generate lift, right, by spinning propellers, or flapping wings. Their thrust vector is always vertical with respect to the robot body. So in order to go to accelerated sideways, what they do is they change their orientation. They generate torque to change their orientation. So they have horizontal acceleration component, right, in the horizontal direction. Now, our revolving wing robots, turns out we don't actually have to do that. Why? Because imagine when the robot is flying, when it's hovering, two propellers will be generating force, right? The same force to keep a constant rotation. Now, suppose we would like the robot to go to the right. What we could do is, since the robot is rotating, so at the moment when the robot is in this in this orientation that you can see here, you can actually increase the force of this upper propeller and reduce the force of this upper propeller of this lower propeller. That doesn't change the spinning torque. That doesn't affect the spinning torque, but it will create unbalanced force that moves the robot to the right-hand side. So we can use this horizontal force to actually control the position of the robot directly. So as a result of that, of course, we could do, for example, in this case, trajectory following flight. I'm not gonna lie that the performance, the precision, accuracy is not gonna be as good as quadrotor, because we actually still need to use the fact that the robot is rotating, and we have to kind of time the force at the right moment in order to move the robot. But it can actually realize the desired trajectory rather well, right? Another example that we showed in the manuscript in the paper is that we can use the constant rotation of the robot to our advantage. Meaning, if we put time of flight sensors or laser rangefinder into the robots, we use the fact that the robot is constantly spinning. Then we can actually create a map of how far, right? We can create a map of the surrounding using the fact that the robot is spinning. So the laser will be sensing the distance to the wall in different directions around the robot, right? And this works the same way as a LiDAR sensor that people use, put them on autonomous driving cars, because for a regular LiDAR sensor, they have very similar sensor, right? That they have to put it on a rotating stage to actually get a 3D information. So in this case, our robot is actually the rotating stage already. Or of course, in this case, since our robot is extremely efficient, it can also carry an insane amount of payload. For example, the 35-gram robot can carry on top of that 21-gram camera package. And honestly, this 21-gram camera package is not efficient at all. It's a really heavy camera, but the point is our robot can carry that, right? So with a camera that is being carried by the robot, for example, we could time the shutter. We could synchronize the shutter with the rotation to get 4 different views at the same time to construct a low frame rate video, for example. This is one possibility, right, to show that, hey, despite the robot is rotating, it actually still can be useful depending on what you would like to do with it. So I'm actually running out of time here. So I'm just gonna maybe show you one spin-off project, what we learned from this work. We also created, for example, a quadcopter that splits mid-air during the flight and becomes 2 bicopters that they can be independently controlled. And so I'm gonna go through this very quickly. So since I don't have time, I'm gonna show you a few slides. The idea is that we would like to, our research team, what we're interested in is we would like to maximize the functionalities of small robots that are, limited by weight or power. So we want to do more. So we show, for example, a robot that can morph, right, without extra actuators, but by the interaction with the environment. Or this robot that can actually, that will not crash into a wall without doing any detection or vision sensing, no extra actuators. Or this robot, again, that can fly or roll, again, with only 4 actuators. So it actually doesn't have extra actuators. So we achieve like more functionalities without added weight or added components on the robot, okay?